So we are talking about moments because we are talking about we are going to talk about bodies already. Up to this point, we have been talking about particles, and particles is just a point, as we saw in the previous last time, where the dimensions don't matter. Because for a particle, the rotation doesn't have a meaning, but for bodies, rotation have a meaning. The rotation of a body has meaning, but the rotation of a particle doesn't have a meaning. And in order to do rotation, we saw that we need a force and a distance. Only if I have a force applied at a certain distance from a point where the body can rotate, then there is rotation. You have a force and you have to have distance. That distance is called lever arm. And so we have to have a point about which there will be rotation. We have to have a force and we have to have distance. So remember that the distance has to be at 90 degrees from the line of action of the force. Very important concept. If you don't have the distance at 90 degrees from the force, then you have to find it. Because suppose you have this, you have point A, point B, let's say point B is the point of application of the force, and you have the distance in this direction. That is not 90 degrees. So this D doesn't work. So you have to find the distance at 90 degrees. So somehow you have to find this distance here. This distance is the one that will work at 90 degrees. If you cannot get the distance at 90 degrees, then you can eventually, you might be able to find the components of the force. Let's say you have this distance here. And this is the point of application of the force B. And this is the force here. So remember what you do here. You can take the components of the force. Let's say we can get here a component that is perpendicular to that line D, and the other that is parallel to that line D. So with these components, let's say call this Fn and this F parallel, and this is point B. Then here you can calculate the moment. The moment of F with respect to A will be just Fn times D. And you can say also that here, in order to be strict about it, then you can say that is plus Fp times 0. Remember why that's 0, right? That 0 is because the force P, the point of application of force P and P, the line of action of force P, it goes aligned with the distance D. So it passes through point A. So the distance from point A to the line of action of Fp is 0. So this moment is 0. So that's why this moment is just the normal force multiplied by D, because this angle is 90 degrees. Okay, I believe you should have that very clear from previous lecture and from previous examples, and you probably, I hope you guys went over the exercise that I recommended for you to do. And we are going to continue talking about moments. So the first thing that I'm going to do here is to talk about how we can move forces around, because now that we are not talking about a point anymore, Because when you are talking about a point, all the forces go through to the point. There is not much to do about it. But now we are going to start talking about a rigid body, a complete body. The forces can go in different locations, in different places, and we might be able to need to move around the forces in order to facilitate the calculations. So let's see what forces we can move and how we can move them. Let me do a drawing here. Let's see, we have this figure here. Let's say we have something like this. If this is a rigid body, and you have, let's say you have a force F applied here, let's call it F1 here, and you have another force F2 applied here. And this is the line of action of the force. These two forces go through the same line of action. If this is a rigid body, then the summation of forces in the X, let's say this is the X axis, in the X direction here will be equal to F1 plus F2. Well, F2 will be in the other direction, will be minus F2. And if this is in equilibrium, then this should be equal to 0, the F1 equals F2. In this case of a rigid body here. If I move these forces through the line of action, let me copy this here. And let's say that we move force 1, if we move force 1 and we put force 1 here, force 1, and we move force 2 here also through the line of action here, force 2, force 2. The situation keeps being exactly the same. If you do here summation of forces in the X direction, you still have F1 minus F2 equal to 0, so F1 equals F2. Nothing has changed. We can move the forces along the line of action and nothing happens. This is only if we have rigid bodies. If we don't have rigid bodies, let me see if I can copy this again. Okay, good. If we have a deformable body, then let's say we have the force 1 here again, and the force 2 here again, force 2. If this is a deformable body, then this will go something like this. Because of the action of those forces, right? And this eventually will make some cracks over here, probably because of the tension and stress there. This is a concrete frame. That's what will happen with this deformable body. If you move the forces around, let's say that let's do another figure here. If we move the forces along the line of action, and now we have the force 2 here, the force 2 here, and the force 1 here. Now the situation is going to be very different. Now this is going to do something like this probably. And now it's going to have some cracks around here, right? So if the body is deformable, then in the first case, we'll have to do reinforcement over here in this section in order to avoid the cracks. And here is going to have the reinforcement of the lower part in order to remove those cracks. So it's completely different situation by applying the same motion of the forces through the line of action. So for the deformable bodies, we have to be careful how we move the forces, even if it is along the line of action. But this is not a problem in our class here. We are working with rigid bodies, so we can do this. We can move the forces along the line of action, no problem. It's what I should call a sliding sliding forces. Our forces can slide, sliding forces. We have sliding forces. While we work in this class with rigid bodies, we are only interested in the equilibrium and not the deformability of the bodies. We can have the forces to move along the line of action. Forces can move, how can I say that? You can move the forces, you can move forces along their line of action, their line of action, and no problem, no problem. So wherever you have a force, you have force here. If you don't like it there because for some reason you need it somewhere else, well, you can move it along the line of action and you can put it in another place and okay. As long as it is along the line of action, you can move it, not a problem. Now, what happened? Let's put here another example. Let's say that you have a body like this, because now you're gonna need to move forces around in order to do your calculation. Let's say that you have the force P over here, but in this location, the dimensions are not easy to see or whatever, then you might need to move the force and put it in here, P. So P can go from here to here, okay, no problem. You can move it along the line of action, no problem. Let's say that here you have this dimension or whatever, or you know these dimensions over here very well. So for some reason you rather have the force located in here instead of here, you can do it, not a problem. Now what happened if we want to move the forces outside of the line of action? Let's say that for some reason you want to move the force here in this new location. So let's see what happens. That is not as easy. You cannot move forces out of the line of action as easy. So what happened? So we need to talk about moments now. Let's put the same this figure here. Let's put it a little easier. Let's see that you have a force here, F. This is the line of action of the force. If for some reason you need to move that force over here, let's say this was here on a point A, and now you need to put it on point B. You want to move the force from A to B, and there is a distance D here, D. So you have to be careful in order to do that motion, because what happened? The force F, it produces some kind of effect of motion to the right? And with respect to point B, it also produces some kind of rotation. You can feel like there is some sort of rotation here due to the force F with respect to point B. So there is actually a moment here on point B produced by force F. So if you want to move the force F to point B, you can move it. You can move it, right? But you have to also, you have to pay a price. You have to put the moment that the force was applying on point B when the force was in the previous location. So let me, maybe it's better if I make another graph here next. If I have this situation on the left, if now I have this situation on the left is the force right here. If I want to put the force here, now I have to include a moment that the force F was producing with respect to point B. and that moment was F times D, and this will be force A. So these two systems are equivalent. I can work with this system on the left, or I can work with this system on the right. Those two systems are equivalent. So if you, for some reason, you need to move the force F to a different location, so you have to be careful, because the force F, it was producing a moment with respect to the new location. So when you remove the force from point A, that moment will not be applied over point B anymore, because you remove the force from there. Now you put it here. So here there is no moment. This force is not producing moment with respect to point B. So you have to apply the moment. Additionally, to moving the force F to point B, you have to apply this moment, and the magnitude of that moment has to be equal to the moment that the force F was applied on point B when it was in the original position. Okay, so be careful with that. We have to deal with that from now on, because we're going, as I said, we're going to move forces around, and we're going to do some examples. Calculate, if you have a system of forces, calculate a different system of forces equivalent to the first one, but in a different position. You have to pay that price. You have to apply an extra moment every time you move a force. I'm talking about this concept about moving a force out of the line of action. I am moving the force out of the line of action. If I move the force out of the line of action, I cannot just move it. When I move it, I have to pay a price. I have to apply a moment because of the motion outside of the line of action. The force, it was applying a moment with respect to the new position. So when I move the force to the new position, I have to apply artificially, let's say it's artificially, I have to apply a moment to compensate for the fact that the force in the new position is not applying that moment anymore. So in order to have the same conditions, I have to have the force in the new position plus the moment that it was previously applied due to the previous position of the force. Okay, and the moment is equal to the force times the distance to the new position. Let's do a first example with numbers. Actually, well, let's put some numbers to this guy here. So let's say I have this force F that has a value of 20 newtons. Let's put it here, 20 newtons. And let's say that each one of these squares is 1 millimeter. 1, 2, 3, 4, 5, 6. This distance is 6 millimeters. And for some reason, I want to move that force from that location A to this location B. So now the force is going to be here. F is going to be here, 20 newtons. So if I am going to move that force from location A to location B, here, this force produced with respect to B a moment that is equal to the moment of force with respect to B in the original position is equal to F times D is equal to 20 newtons times 6 millimeters, so equals 120 newtons millimeters. So if I am going to move now the force F to this new location here, in order to keep this effect of this moment that it was applied here on point B, I have to apply the moment here of 120 newtons millimeters. All right. So again, this situation here is equivalent to this situation. And if you need to do calculations on this, you can use this diagram here, or you can use this diagram here. Both of them are exactly equivalent. So you can do that trick. Probably you have some kind of condition due to the new position of point B, that you rather have the force at point B than at point A. Well, you move the force to point B, but you have to apply the moment.